Hi everyone, this is Selva. So in this one we will see a very interesting concept, Cook's distance for outlier detection. So first we will understand the concept, the entire concept behind Cook's distance very clearly. Once that is clear, we will see how to use it for outlier detection, or to be more precise, for influential points detection. Now, why do I call it as influential points more precisely is because whenever someone talks about Cook's distance, it's always associated with the training or a building of a machine learning model. It's always associated with a specific machine learning model. So let's try to understand what this is all about. We will understand this with an example. Alright, so let's take a data set, very easy to understand with data set involved. So let's take a data set. Alright, so it has lot of different features. I'll tell you what these features are, and it has a lot of rows also. Alright, let's imagine this data set contains information about car models. It has various technical information about various car models. So each row here represents a given car model. Let me call it as C1, C2, C3, C3, C4, so on and so forth, till Cn, n different cars. And we have cars features such as the torque, horsepower, mileage, all these different information is present. We also have the price of the car also in the end. All this information features is present, and we also have the price. Now for this data set we want to know which of these cars are sort of extreme, or in other words outliers. In order to do that, you can use Cook's distance, of course, and because multiple rows, multiple columns are involved, multiple features are involved, this is again a multivariate approach of finding out outliers or influential points. Now, in order to compute Cook's distance, let's try to understand what's the formula and how to go about computing the Cook's distance. The first step is the building of a machine learning model. Now, in order to build a machine learning model, you need a predictor and a variable that you want to predict. Alright, so in this case, we want to predict the price of the car using all the other features that influence the price, the car's dimensions, all the various features of the cars influence the price, isn't it? So all these other features present in the data act as the predictors. We will call it as X. The variable that we want to predict, which is the price, we call it as Y. Alright. So first step, typically whenever we are talking about Cook's distance, it is always associated with a specific type of machine learning model, which is nothing but linear regression. It is always associated with linear regression. Alright, so the first step is, now we know what variable we want to predict. So using stat models in Python, we will first build a linear regression model using the given x, the entire set of the x variables, and the y variable. We will call this as LR1. First we will build a linear regression model, we will call this as LR1. Alright. Now using LR1, we will make the predictions. You have trained the model now, we have trained the model. After training this, we pass in all the x alone, the x data alone as an input. So this is, I'll mark this in red to distinguish this. This is y, this is the actual value of price data, isn't it? So we will pass in all the x variables alone. We will pass in all the x variables to the linear regression model LR1. Why I am calling it as 1? Because we are going to be building another linear regression model shortly. Right? So we pass this as an input to LR1, and we will get the predicted values from the model, which we will call it as y hat. So that y hat, let us mark it here. For every other row in this data, every other car model, we will have a predicted value of price, which is y hat. So this is the first step. Alright, this is the first step, prerequisite for computing Cook's distance. So we have this. Second step is we want to know amongst all these cars, which of the car models, which of the rows present in this data exerted the most influence in coming up with the equation inside the LR1 trained linear regression model. How do we find that out? We want to know which of these cars are most influential. That's basically it. In order to find this, what we will do is, we want to find basically the Cook's distance of this particular car. That's what we want to find. We will find the Cook's distance for all the cars whichever car is having the largest Cook's distance, they are going to be the outliers or the most influential points. Okay, so we want to find the Cook's distance. All right, to how to compute that? In order to find it for this particular car, what we will do is we are going to retrain the model. We are going to retrain another linear regression model. We will call it as LR2. We are going to retrain this whole thing one more time, but this time we are going to leave out this particular row. We are going to leave out this entire row and retrain it with all the remaining rows present in the data. By doing this, the linear regression equation might be slightly different. This will have one equation, this will be a trained model, this will be another trained model, but the regression equation, the coefficients will be slightly different for both of these models. Alright, now again we are going to pass in the x values. We will pass in the x values. I hope this is legible. So we will pass in the x values as an input to this linear regression model and get the output in this case, which we will call it as y hat I. Now we will add another column in this data. We will call it as y hat I, and we have this for all the different rows. We will ignore this row for computation purposes. We will ignore this row also in this case. All right. So you have two separate predicted values: the predicted values from the model that has all the data points, and predicted values from the model that did not have the data point I. Two separate values. We will now use both of this to compute Cook's distance. The equation of Cook's distance is shown here. So this is the entire equation. How to read this? This is the y hat that we just predicted is here. The y hat we just predicted is y hat j. All right, for where j goes from 1 to n. We are going to sum this all up for all the rows. We are going to be repeating the same procedure for all the data points in the data set. All right, so y hat j, and then you have y hat j excluding the data point I, excluding this particular data point I. Right, we have both of these columns. From y hat we will subtract y hat I. That's what we are doing here. Do this for all the other rows in the data set also. We will subtract it, square it up, and do the same thing for all the rows present in the data set. So this involves retraining your model as many times as there are rows present in the data. Got me? So we will be retraining it as many times, sum it all up, sum up all these square of these differences and divide it by the number of terms, number of coefficients. So this model, suppose if we have 5 different x columns, 5 different columns in this model, we will have p equal to 5. And MSE is the mean squared error, where you have the actual value of y, which is the price. You have the predicted value, this original predicted value, which included all the data points included in the training, right? So that y hat we have. Subtract this, so y minus y hat, subtract this, that will be the error term. Square this up, squared error. Sum it up for all the rows present in the data and take a mean. That is mean squared error. So this is the entire formula for computing Cook's distance. Those data points that is having a large, very, very large values of Cook's distance, those are the most influential points. Hope this entire concept is clear. So to simply put it, you have a data set, compute the predicted values of y for that data set, right, including all the rows, then compute the predicted value of y for all the rows in the data set, excluding I, excluding the data point for which you want to compute the Cook's distance. All right, you have trained 2 separate models, computed the predicted values, subtract them, square them up and take the mean. So this whole thing, this whole term here, this is not the mean, this is the summation of the entire squared errors, and divide the whole thing by the number of coefficients and mean squared error. That's all there is to Cook's distance. Let's now try to implement it in Python. So first up, we are importing all the necessary libraries. We are importing pandas, numpy, matplotlib.pyplot we will use for plotting purpose. Both of them are used for data wrangling and data manipulation. Then this is for displaying the charts. All right, so all clear. Now the data set that we will be using is present in this location. I will leave a link to this in the description. So this location, the entire data set is present. Now if you look at this, This is a data set that is present in the UCI machine learning repository. So this is a huge collection of data sets, right? This is the exact homepage of archive.ics uci.edu. This is a huge collection of machine learning data sets, very nice standard data sets. From this, the exact data set, the link here, this is the exact link to the data set. If you enter this link, you should get this kind of a screen. Otherwise, right? So all these are the different data involved that we are going to be using here. So this we are importing it using pandas. pd.read csv, pass in this URL as the file name, names equal to header. These are the names of the different columns present in the data set. All right. So we have the data here. All right. At the end of it, you should be having the price column. This is the column that we want to predict. Then include only some of the data that we want to include. You can all include everything also. All the numeric data if you have, you can include those data. Replace the question marks with nan values. Drop the rows that contains nan values. Reset the index to start from 0, 1, 2, 3 and so on. And this is how the data set looks like. Alright, this is how the data set currently looks like. On this, we will be building the first linear regression model. So to do that, we are importing from statsmodels.api, importing this object as sm. Define your y variable, price, and all the x variables. So we have defined two different data sets, data frames. Add a constant. This will add an intercept term, just a new constant. So what this will do is you have the data set here, you have the entire data set here. Add constant will add a new row here which contains the value 1 for all the rows. That's what this one does. This command does. All right. This is for including the intercept when you are building the linear regression model. It's up to you. This is an optional statement. Once this is done, use sm.ols, ordinary least squares. This is the algorithm that SM uses, stats models uses to build the linear regression model. So pass in the y first, then the x. We are storing it as floats, by the way, and dot fit here will do the training part. So the model gets trained and gets stored in the model object. All right. So after that is done, the model is trained now successfully. That's all there is to it. From this model object, we are going to directly extract the Cook's distance value directly. All right. So then we are importing the numpy, set print options, suppress equal to true. All right. So this is for display purposes. Basically, it will not make the scientific form. It will not show the scientific form. It will show the full float as it is. All right. So if you get from the model object, it contains a method called getInfluence. This object, on calling this function will specifically compute the Cook's distances of all the rows, and we are storing it in this particular object influence. Now from influence, we are extracting the Cook's distance and storing it under Cook's. Printing Cook's, this is the entire value of Cook's distance values of the entire data set. Then we are going to visualize the Cook's distance using matplotlib. If you plot it here, right? If you plot it here for all the different rows in the data, the y-axis here is the Cook's distance. You can see certain observations, like this one is a very, very super influencer here. And these few observations are also influences, are also good influences. But if you want to consider any data point as an outlier, it is going to be this particular data point. These are the next highly influential data points. All right. So with that understanding, you can extract a typical standard convention is those data points that are more than 4 times the Cook's distance, 4 times the mean Cook's distance. So first we will compute the mean of the Cook's distance for the entire data set. All right, so this seems to be the mean. We will multiply this by 4. Any data point that crosses this threshold is a common convention to call those outliers as extreme data points or outliers. Call those data points as outliers. But some data must be different. All right, let's look at it. So symboling, it has value 3. Here it is, it's having all the values. Wheelbase. Okay, these two guys. Engine size and bore. 121 and 2.54. If you look at this, the engine size and bore, this was 121 and 2.54 here. All right. So collectively across all the rows, all the columns present in the data, might have been picked up as an extreme value. So this particular data point is not so different from the non-influential data points. Maybe it is around the cutoff. Let's quickly check that also. So okay, here, so this is 124, right? This index is 124, and you look at this in this chart, the 124th data point is very near to this line. All right, so the chances are this is also very in the borderline of being considered as an influential data point versus a non-influential data point. All right, so but if you look at the values that are having a very high value of Cook's distance, you will definitely see those kind of data points are very different from the rest of it. So that's how we compute Cook's distance. I'll see you in the next one, where we will cover another very interesting approach.